Welcome back to another video by Adeptis Academy. Ever wondered what's happening inside your favorite gadgets? It's not magic, it's circuits, guiding electricity to make things work. Think of a circuit as a mini road system for electricity. To understand these pathways, we use special tools, like detectives searching for clues. Analyzing circuits helps us figure out how things work, why they don't, and how to build our own inventions. It's a skill for anyone curious about the world, not just engineers. Imagine building a simple circuit to light an LED, but it doesn't work. Is the battery dead? Is the bulb broken? Circuit analysis helps you find out. Instead of guessing, you use measurements to pinpoint problems. Every circuit is a puzzle, and you're the detective. Let's get ready to explore the invisible world of circuits with the right tools. Your adventure into electronics starts now. Let's begin. To become circuit detectives, we need a toolkit. Our three key tools are the multimeter, oscilloscope, and signal generator. The multimeter is the Swiss Army knife of electronics, measuring voltage, current, and resistance. It gives you quick, direct numbers, perfect for basic checks. The oscilloscope is more advanced. It draws a picture of how electricity changes over time. It lets you see waveforms, how signals wiggle, pulse, or change shape. The signal generator creates signals to send into circuits, letting you test how they respond. You can make different waves, like sine or square, at precise frequencies. Each tool tells a different part of the story. Together, they help you see, measure, and create signals. Don't be intimidated by the buttons and dials. They're here to help. Let's meet our first tool up close. Meet the multimeter, your go-to for basic measurements. It answers three questions. What's the voltage? How much current? What's the resistance? To measure voltage, connect the probes in parallel with the component. For current, break the circuit and place the multimeter in series. For resistance, remove the component and let the multimeter send a tiny current through it. It's like checking water pressure, flow, and pipe width, all in one device. The multimeter is also great for checking continuity, seeing if a wire is broken. With just this tool, you can solve many circuit mysteries. It's simple, powerful, and essential for every electronics explorer. Let's see it in action with a real experiment. Let's explore electronics with a simple experiment, lighting an LED. This basic circuit teaches us about electricity flow and component interaction, a great starting point for anyone curious about electronics. Get ready to build and learn. You'll need a 9V battery as our power source. Ensure it's fresh for optimal results. Next, an LED, light-emitting diode, will produce light when electricity flows through it. A standard red LED works perfectly. A 470 ohm resistor protects the LED from excessive current, preventing damage. Resistors limit electricity flow, ensuring safe LED operation. Finally, a breadboard allows us to connect components without soldering, making circuit building and modification easy. Before building, check your battery voltage to ensure proper functionality. Set the multimeter to DC voltage mode, typically indicated by V with a straight and dashed line. A 20V range is suitable for a 9V battery. Touch the multimeter probes to the battery terminals, red to positive, plus, black to negative. Confirm the display reads close to 9 volts. A reading between 8.5V and 9.5V is acceptable. Now, build the circuit on the breadboard, connecting components carefully. First, connect the resistor to the positive rail of the breadboard, marked with a plus sign. Connect the other end of the resistor to the LED's long leg, positive side or anode. Connect the LED's short leg, negative side or cathode, to the negative rail, marked with a yaw sign. Connect the battery to the breadboard's power rails using a 9V battery clip. Red wire to positive, black wire to negative. If the LED lights up, your circuit works. Double-check connections if it doesn't. Use the multimeter to understand the voltage in the circuit. Measure the voltage drop across the resistor and the LED to see how much voltage each uses. Measure voltage across the resistor by touching probes to each side. Measure voltage across the LED by touching probes to its legs, red to long, black to short. Add the resistor and LED voltages. The sum should approximate the battery's voltage, around 9 volts. This shows how voltage is shared. The battery provides total voltage, and components consume portions. These measurements reveal how each component contributes to circuit behavior. You've built and analyzed your first circuit. Ready to explore more complex circuits? Some circuits have signals that constantly change. This is where the oscilloscope shines. Unlike a multimeter's single number, the oscilloscope shows a graph of voltage over time. You see the exact shape of a signal, its amplitude, period, and frequency. The screen's grid helps you measure voltage and time precisely. The probe listens to the circuit, and the oscilloscope plots thousands of samples per second. It's like a high-speed camera for electricity, revealing every fluctuation. You can spot smooth sine waves, sharp square waves, or noisy signals. The oscilloscope turns invisible electricity into something you can see and understand. Let's use the oscilloscope with a real signal, moving from theory to application. Use a function generator app on your smartphone to play a 440 Hz sine wave. Connect your phone to the oscilloscope using a headphone cable. Strip the headphone cable to expose the wires. Connect the signal wire to the oscilloscope probe and the ground wire to the oscilloscope's ground clip. Power up the oscilloscope. Adjust the volts div and time div controls to set the voltage and time scales. Fine-tune until you achieve a clear, stable sine wave. Measure the peak-to-peak voltage by counting vertical divisions and multiplying by the volts div setting. Determine the period by counting horizontal divisions for one cycle and multiplying by the time div setting. Calculate the frequency using frequency equals sine 1, period. Compare the calculated frequency to the 440 Hz set on the app. You're now visually confirming voltage and frequency, a powerful skill in electronics. This hands-on approach transforms abstract concepts into observable phenomena. With practice, you'll develop an intuition for waveforms, enabling you to troubleshoot circuits. Now let's create your own signals using a function generator. Now, meet the signal generator, the tool that creates signals for your circuits. It lets you choose waveform shape, frequency, and amplitude. Want a smooth sine wave or a sharp square wave? Just select and set the values. It's like a wind tunnel for electronics, letting you test circuits under controlled conditions. For example, send a 1 kHz sine wave into an amplifier and use the oscilloscope to see if it's amplified or distorted. Change the frequency to test different responses. The signal generator makes experiments repeatable and reliable. Just connect its output to your circuit's input and start testing. With this tool, you become an active experimenter, not just an observer. The real magic happens, the kind that unlocks the secrets of electronics, when you use all three tools together: the signal generator, the oscilloscope, and the multimeter. Each plays a vital role, but their combined power is truly transformative. It's like having a symphony orchestra at your fingertips, each instrument contributing to a harmonious understanding of your circuit. Imagine testing a low-pass filter, a fundamental building block in countless electronic devices, designed to let low frequencies through and block high ones. It's a gatekeeper, carefully controlling which signals pass and which are rejected. Understanding how it works is crucial. Use the signal generator, your source of controlled electronic signals, to send a sine wave into the filter. This sine wave acts as our test signal, a known quantity that we can use to analyze the filter's behavior. Connect the oscilloscope to the output, acting as your eyes on the circuit to watch what comes out. Observe the waveform, its shape, its amplitude, and its timing. This is where you'll see the filter's effect in real time. Start with a low frequency, a gentle hum, if you will. The output wave should match the input. At these lower frequencies, the filter should allow the signal to pass through relatively unchanged. Increase the frequency, slowly turning the dial and exploring the spectrum. And watch the output shrink. The filter is working. You'll see the amplitude of the sine wave decrease as you approach the filter's cutoff frequency. Use the multimeter to check voltages, confirming your power supply is stable, and ensure everything's powered correctly. A stable power supply is the foundation of accurate measurements. This method, stimulus in, response out, a fundamental principle of circuit analysis, is fundamental in electronics. By carefully controlling the input and observing the output, you can characterize the behavior of any circuit. Always work safely. Safety is paramount when working with electronics. Use low voltages and never test wall power. High voltages can be dangerous, so stick to safe levels. Be curious, experiment, explore different components and circuit configurations, and don't be afraid to turn the knobs. Adjusting the settings and observing the results is a great way to learn. Every circuit you build is a new discovery. Each connection, each component, each measurement adds to your understanding. Keep learning, and you'll be amazed at what you can create. The possibilities are endless, from simple circuits to complex systems. Your journey into the world of circuits has just begun. Embrace the challenge, enjoy the process, and prepare to be amazed by the power of electronics.